This is Pre-Calculus Concept 18C. We're going to be talking about the number E today. Yes, I know that E is a letter, but it also is a number, and for a lot of you this will be new. Turns out that a lot of exponential functions end up involving the number E. The definition of E is it's the value of the expression 1 plus 1 over n raised to the nth power as n goes to infinity. I put a little screenshot here of a calculator with a couple examples. If you plug in 1 for n, you get the number 2. If you plug in the number 2 for n, you get 2.25. And as you grow and get bigger and bigger and bigger, it seems like the expression would just go to infinity, but it actually starts to level off to a certain value. So 1 plus 1 over 10 to the 10th gives you this decimal. And if I go all the way up to 100, I get this decimal. And you could keep going, going. But what turns out to be true is that E is an irrational number. Remember that that means a number that never repeats and also never ends, just like pi. And the approximation is about 2.718. And that's a good number to kind of remember, just like pi is about 3.14. But ultimately, when you see the letter E in a math problem, it really represents a number, and so you should think of it like the number 2 or the number 5. Alright, so the graph of e to the x power is really just another example of y equals b to the x, like you learned in the previous lesson. So we would expect a graph that has all the same properties as y equals b to the x. So the domain is all real numbers, the range is y values greater than 0, you have an x-intercept of 0, 1, you have a horizontal asymptote at y equals 0. But basically this is a good graph to remember. E to the x is kind of known as the natural exponential function, and it will behave rising to the right and falling, or sorry, leveling off there to the left, and that is the natural exponential function. Alright, so again, a lot of word problems, exponential function problems have E in them, and oftentimes we'll see it in money growth problems and also population growth problems. So here's a little problem we're going to look at kind of in depth. So up at the top here is a function that's going to model a population, in this case wolves, in the northern Rockies. So 1.26e to the 2.47x power is going to give us the number of wolves x years after 1978. So this was an endangered species. Back in 1978 they started tracking it to see if the wolf population was growing. So our question is, how many wolves are there in the year 2010 according to this model? Right, so a big part of this problem is that x is defined based on a certain year. In this case it's 1978. So I actually have to figure out that 2010 is a certain number of years after 1978. So if I do a little subtraction problem, I'm going to get 32 for that. So that's going to be my x value. X is going to be 32 years after 1978. So the 2010 question is really going to be f of 32. There's a lot of ways we could do this. You could make a graph on your calculator and take a look at the population over several years. You could make a table on your calculator. Since it's asking for a specific year here, I'm going to just go ahead and plug in 32 into my calculator. Okay, again, be careful about order of operations. I want to do the exponent before I do the multiplication here. I also, since I have two parts to my exponent, when you type it in your calculator, you want to make sure you kind of think about that as a product before you actually raise it to that power. So it's e raised to that entire product. Alright, so typing that in, you get about 3,412 wolves. So just in about 30 years, that population has grown from a very small amount of wolves to over 3,000, according to this model. Okay, box 4 is going to be a U-try. We're going to take the exact same model for the wolf population and just ask you to figure out a different year. So if we use the same exact model, 1.26 e to the 0.247x, and ask you what was the wolf population in 1995. Take a minute, use your calculator, see if you can figure out that answer. Alright, so 1995 was year 17. You get that by subtracting 1995 minus 78, and so f of 17 is the value that we're looking for. If I take 1.26 e, raise it to the product of 0.247 times 17, I get an answer of about 84 wolves.